This cell reorders all the dimensions of a tensor using permute. A common use case is converting image data from NumPy HWC format to Pytorch CHW format for processing in convolutional networks. Torch.cat concatenate tensors. In this cell, I concatenate two tensors along row using dimension equal to 0 and column using dimension equal to 1 with torch.cat. Concatenation combines tensors along an existing dimension without creating a new one. Next cell is torch.stack, stack tensors. This cell stacks multiple 1D tensors into a 2D tensor using torch.stack, which creates a brand new dimension. Stacking is how individual samples are assembled into a batch for training. Next is matrix multiplication, which is three ways. Here I multiply two matrices using the at operator, torch.mat multiply and torch.mm. All three give identical results and the at operator is the most concise and readable for matrix operations. Next is batch matrix multiplication. This cell performs matrix multiplication across entire batches of matrices at once using torch.mat multiplication. Pytorch handles the batch dimensions automatically, making it efficient for neural network forward passes. Next is neural network layer, which is y is equal to xw plus b. I simulate a full linear neural network layer by multiplying input x by weight w and adding bias b. This is exactly the forward pass computation of torch.nn.linear done manually. Next is dot product. This cell computes the dot product of two vectors using torch dot dot, which is the sum of their element-wise product. The dot product equals 32 here and is equivalent to a into b dot sum. Next is vector norms. Here I compute L1, L2 and an infinity norms of using torch dot norm. The L2 norm gives the Euclidean length and normalizing a vector by its norm gives a unit vector used in cosine similarity. Next is matrix properties, trace, determinant and inverse. So let's go for it. Yeah, this is the cell. This cell computes the trace, determinant and inverse of a 2 cross 2 matrix. I verify the inverse is correct by multiplying A by its inverse to confirm. We get the identity matrix back. So next is matrix decomposition, which is eigenvalues and SVD. I perform eigen decomposition using torch.line alg.ike and singular value decomposition using torch.line alg.svd. These decomposition are used in advanced topics like PCI and detection analysis. Next is einsum sum and identity. This cell introduces Einstein summation notation using torch.einsum. The notation I sums all elements of a 1D tensor and I simply returns the tensor unchanged as an identity operation. Next is Einstein sum transpose and row sum. Here I use Einstein sum to transpose a matrix by swapping indices ij to ji and to sum along rows with ij to I, and sum makes complex tensor operations compact and readable with a single notation. Next is einsum with diagonal and trace. This cell extracts the diagonal of a matrix using with I and computes the trace using II by repeating the same index for both dimensions. Einsum naturally selects the diagonal elements. Next I use einsum for element wise multiplication, as you can see, and for the dot product with I. The presence for absence of the output index determines whether the shade dimension is kept or summed away. Next, this cell performs matrix multiplication using einsum with a notation of ik, kj and with ij. This shade index k is the contracted dimension and the result matches exactly what a at the rate b produces. Next, here I use the einsum to perform batch matrix multiplication where b is the batch dimension. This is equivalent to torch.bmm and is common pattern in transformer models. Next is this cell performs the core of the attention mechanism using a einsum to compute q at the rate k to the power k to t scores. The notations which we can see here is efficiently computes the attention scores between all query and key positions. Next, I implement and compare 4 activation functions using this is the one cell function using torch dot okay, let me just see torch.nn functional, and RULU is the most popular for hidden layers, sigmoid for binary outputs, tanh for zero centered outputs, and leaky ReLU to fix dying neurons. Next, go to next cell. Here, softmax activation happens, where this cell applies softmax to raw logates to convert them into probabilities that sum to exactly 1. Softmax is used in the final layer of multi-class classification models to produce a probability distribution. Next, here I compute MSE loss for regression using a f.msc loss, and cross entropy takes raw logits and integer class labels directly without needing softmax first. Next, what I am doing in this cell is here this cell applies batch norm 2D to a CNN future map and layer norm to transform sequence. Next cell is I clip tensor values to a specified range using torch.clamp. This is used in gradient clipping to prevent exploding gradients and in activation to keep values within a stable numeric range. Next cell, what I do is I apply Xavier initialization for sigmoid Tanich layer and Keming initialization for ReLU layers. So proper initialization is critical for stable training and preventing vanishing or exploding gradient. Next is autograd, requires grad and backward. Here what am I doing is I perform, what gradient tracking requires is required grad equal to true. We have done that and perform forward computation. Then call.z.backward to compute gradient automatically. The gradient of z is equal to sum x to the power of 2 with respect to x is 2 power x. In the next cell, this shows how a disable gradient computation during a interference using torch.node.grad. This is speed up computation and reduces memory usage since gradients are not needed when we are not training. Next one is one hot encoding. I convert integer class labels into a one hot encoded vectors using f.1hot. Each label becomes a binary vector where only the position corresponding to the class is 1, used in classification targets. In the next cell, this cell retrieves the top 3 class probabilities and their indices using torch.topk. Topk is used in evaluation to check if the correct class appears within the model topk prediction. And in the next cell, here I create a casual mask using torch.tru and apply it to the attention scoring using masked fill. The casual mask ensures that each token can only attend to previous positions, not future ones. Next is padding sequences. This cell pads variable length sequence in the same length using pad sequence, filling shorter ones with zeros. Padding is essential by batching sequence of different lengths in NLP task. The last one is I use tensor.gather to select the logit corresponding to each sample's correct class labels. This is a key operation in cross entropy loss computation and other per sample selection task. That's it with this notebook demo. Thank you.